Ladies and gentlemen, thanks for attending this TED Talk, which is co-organized with the Hong Kong Academy of Engineering Sciences. TED Talk is a series of forums dedicated to foster innovation and related topics. Today we are very privileged to have a distinguished scholar, Professor Xiang-dong Lee, as our esteemed speakers. Professor Lee is a distinguished scholar and expert in the field of environmental science and sustainable urban development. Currently serving as the Dean of the Faculty of Construction and Environment and the Director of the Research Institute for Sustainable Urban Development at the Hong Kong Polytechnic University. Professor Lee holds an esteemed position as the Chair Professor of Environmental Science and Technology and the Goh Ming Professor in Sustainable Urban Development. Professor Lee's research interests primarily focus on the regional environmental pollution, urban environment, and sustainable technology. His contribution to this area has been recognized through his involvement as the principal investigator of numerous research projects which have been funded by prestigious organizations such as the RGC, NSFC, and the UGC Area of Excellence Scheme. In addition to his extensive research endeavor, Professor Lee has made significant scholarly contribution by publishing more than 250 papers, primarily in leading international journals. His exceptional research performance and dedication to advancing the field of environmental science has earned him the esteemed Claire C. Patterson Award from the Geochemical Society in 2022. Without further ado, please join me in welcoming Professor Lee.
Thank you very much, Professor Leung, for the nice introduction, and also thanks you for Professor Yuguo Li, Professor Nei for organizing this Hong Kong ES talk. I actually thank you for about our friends, particularly our Hong Kong U, like civil engineer friends. Anyway, we have Xiaoyang and Keming, and also for Xiang and Zhang Tong to join. I would just talking about some of our recent years study for about the air pollution and human health issues. And it's great we have quite a number of collaborators, particularly in Hong Kong U and as a School of Public Health. And I thinking is the way of try to making, Yuguo told me quite a lot of experience how to talking about a general audience in kind of the public understanding for science and engineering. I hope I try to manage well, and please getting any of your question during my presentation or in the last 20 minutes within about the next hour. Okay, I would just give you just one of the ways, the topic of how clean is our air we breathe in urban area. Particularly, I will use the example for Hong Kong. But if you're going to see one of these really clean air, and in one of these probably 6,000 meters above sea level in the mountain Himalaya, it's nearly reached to the top into Mountain Everest. So that's kind of like a really like a clean air and spot on the whole Earth. But the oxygen level is only 60%. So you won't be nicely breathed there because the oxygen level is too low. So unless you be trained or you be taking medicine. So another one is our urban air. I'm not sure how many of you are liking hiking. So I was really enjoy hiking. So this one photo I was taking probably about 2 or 3 years ago, still during pandemic. You can see the blue sky above, but then reach to the Lion Rock. There's kind of the green air's cap. But during that time, bear in mind, we're still pandemic. So it's not about the full gear of this whatever industry, traffic, or other way. But that's already see in itself the urban air and above the cap, there's a blue sky and over there. So how we actually be as town mouse every day, breathe this air can affecting our long-term health issues. That's I'm going to talking about this afternoon. Anyway, so if we're going to see this one from the WHO about what are the source for air pollutant, and so in the urban area, so there are many of these we all know, including quite a number of like the gas phase, like some of you probably already familiar with sulfur dioxide, NOx, like ozone, carbon monoxide, most importantly, and the PM2.5. One of the very fine particles can affecting our health, can actually change quite a number of this ecological system as well. So, but there are many ways of contribution, even from our industry process into about transportation, waste management, household energy use, agriculture practice into like a natural gas system. So that's the way we need to understand from a scientific engineering point of view, how we're going to control it. So putting that way, I believe for most of our audience, quite a number are expert here. I do not need to introduce you particular through what is PM2.5. But if you are new in this area, I just want to using one of these here and within how many can accommodate PM10. In one of our kind of very fine here, we can almost hosting 5 small particles. But within one PM10, we can have about 4 PM2.5 in dynamic. So in that sense, PM are very small particles, mostly invisible to our kind of like human naked eyes. But they can actually be the #1 issue for about this our general like environmental health. So how about you can see from a WHO statistic, we have a 7 million deaths attributed to this kind of air pollution. So which actually the major one, including about this Asia Pacific. We almost have a combined from Southeast Asia and West Pacific, we have almost 4 million. It's the kind of the most kind of populated nation like China and India, which actually be largely affected by this health event. Okay, if we're going to putting into about time theory to have looking about the issue, you can see from 1990 into about almost 30 years into 2020, we have quite a number of decrease in air pollution, but that's majorly attributed to about the gas phase. Just we mentioned about sulfur dioxide, NOx, and others gas phase. But the outside particular matter level is still flat, including about this ozone level. But if we're going to putting about the different WHO action concentration for PM, you can see I just want you to looking the number is the target 1 is 35 microgram per cubic meters. Target 2 is 25 microgram per cubic meters. And target 3 is 15. Target 4 is 10. But now this one was in 2019. But 2021, the WHO lower standard to 5. So how do you guess our Hong Kong's level? We actually between the target 3 and target 2. So that's target 3 is 15. Hong Kong currently annual level is 19. So we are probably between about, we be better than 75% of world population. But we still actually be like some way away from the WHO standard. But another way is you can see the global death burden rate due to PM2.5 exposure is definitely affecting our senior guy rather than our young population group. Anyway, so that's kind of like the reality. The aging population will be affecting more about this PM pollution. But it's not just a single disease, because a particular PM2.5 pollution affecting quite a number of the health outcome. You can see from this chronic obstructive like pulmonary disease, the COPD is very common in Hong Kong as well, but also is a kind of like a stroke, because there's affecting our blood pressure, can actually causing about health problem. You can also have lung cancer, like heart disease, other ischemic heart disease, even about like diabetes be affected from this exposure to PM2.5, and lower respiratory infection and a few others kind of issue as well. So the X can contribute is environmental risk, almost the top 5 into about global and also in China. And eventually, most of this we are talking about an environmental equality, because like the cheap housing always close to the most significant air pollution area. So where the pricey and market property maybe have enjoy better quality. Even in Hong Kong, the south of Hong Kong Island always have a better air quality compared with the New Territory and some of the very populated like density area. Anyway, so if we're going to see about not only for the health issue, but also we're thinking about the annual cost for health damage, which this one was calculated in 2016 for the income group. You can see how much about there's significantly contribute, not only for about this general hospital like admission and also outcome, but also can really contribute sometimes very significantly 5 or 6% of the equivalent GDP regarding about this absent from the work or affecting about productivity. So that's one of the case we wanted to know. If we want to control and limit this health problem, we need to understanding how much we can control the pollution. So that's just give you one of the top about in Hong Kong. We have like this top 3 emission source for this air pollution. So depend about, you're talking about gas phase like NOx, we have quite a significant of this issue for this public electric generation. We can actually blame to HEC or CLP, or we have this kind of the road traffic consider about currently being the NOx as a major contributor, but also we have this navigation, in other words, the marine traffic. We still have a holding about one of the largest container terminal in Hong Kong, because the marine traffic burning a different like diesels compared with the road traffic. So that's the one we really see. But also the issue is you can see about there's always have a trend, these annual patterns, because winter we always have about this severe worse air pollution compared about this summer season as well. Okay. Putting into these issues, we do have about a significantly control strategy, which is issued by the Hong Kong SAR government, which in particular was responsible by Environment Protection Department, EPD, which you can see how about there's established this kind of reduce the marine emission since like 2012. That's almost 14 years. They have a cutting about this actual SO2 like emission, and now they are actually not #1 contribute for SO2 as a source. It's become the second one. So the first one is still about our coal and gas-fired like electricity generation, but also actually PM10 also have a cutting almost about half. So that's the sole issue regarding. But if we're looking about air pollution, particular ambient air pollution, it's not just only a local city, Hong Kong issue. So we needed to really see them into a regional, particularly in our Greater Bay Area or whatever you call the Pearl River Delta region. This one from Professor Yu's group in the Hong Kong UST's study. You can see how about there is a very significant PM pollution in 2006, 2008, 2010, 12, and compared in the last kind of few years, they are significantly not only improved locally in Hong Kong, but also significantly improved in the regional. So we be benefit for the regional cooperation of the air pollution. And also in Hong Kong, we can see about our improvement locally, also thanks for about 2 power utility companies change. Because usually in back to 2012, about 10 years ago, we still using 50% of the coal as a power generation plant. But now they are reduced almost 1/4. So gas phase increase into 50%. So that's kind of like an issue. You can see the trend change regarding the contribution over from 2001 into the, about almost 20 years. We have about this issue. We have reduced our PM 2.5 from about 35 to 40 microgram per cubic meter into about 16 to 19 milligram per meter, almost cutting to half. So that's like the issue. But how about this kind of cutting total like pollution level convert into our health impact? So you can see this one of a recent study which compare about this 2000 and 2004. There's a cancer rates, non-cancer hazard quotient about the different like a chemical component. Compare about 2016 to 20. So you can see how much significantly. For example, the #1 issue for the diesel PM concentration contributes most significantly, #1, but it actually decreased almost 10%, 15% compared within about 20 years ago. So that's kind of, you can see our like achievement by health, which have a premature deaths kind of decrease almost 2,000 people, like hospital admission about 1,500, and clinical visit almost like 500,000 about the reduction level. So that's one we have a huge economic benefit. If you contribute towards about the calculation for formula for WHO is 2.14 to $2.17 billion per year. So that's a really huge amount of the enjoyment. But if we're going to looking about the challenge ahead, do we have like a breath clean air as much as we desired, but not yet? You can see about how in the last 20 years change. So the WHO like 3 years ago just change about this 10 microgram into 5. That's giving our challenge how we really can really fulfill the final target. I think it's Hong Kong probably the same as the Denmark, Germany, and the UK, the green line on bottom. But you can see other countries which actually even mainland China still a bit of a challenge, now reached to about 35, still a bit of way to go. So another way we would putting on is, for example, if even for about Canada and the US, still cannot meet as a kind of a national annual level within WHO standard. So we thinking, even Hong Kong or the Greater Bay Area, we still have another 10 years, 20 years to go. So how are we going to see under the current situation, can we actually have a better health outcome rather than total reduction of the total PM concentration? That's the way. But that's triggering us to thinking is, can we actually, the PM 2.5 is still above 10 microgram per cubic meter, but can we have reduced the most significant toxic component where we can enjoy better like health outcome? So because why we thinking about that way, we can using one of this diagram, this actually diagram from WHO data. Even there's a low concentration, for example, around about 15, like Hong Kong currently, around 20. You see under the 20 microgram per cubic meter average pollution level, we still have around about this PM 2.5 related deaths, around almost 5 times difference. So in other words, if we understanding which can cause the most significant health issue, if we control that component, even the total concentration is still above WHO standard. So we still can actually get a much better health benefit as far as our local control strategy. Anyway, so you can see the challenge we're facing, particular for Hong Kong's issue here. We definitely have still a very small area, have a large road traffic. Although the e-vehicle have increased, but it's only less than 15%. But as we mentioned, the navigation for the marine traffic still contribute that one. We still have the 2 large public plant for about whatever gas and coal-fired, and we have very high concentration of population density. Another issue contribute here, increasing our aging population among the whole city population here. So in deal with that, the government really issue about, I'm not sure how many of you have assessed this report, the Clean Air Plan for Hong Kong, which actually targeting 2035. There are many of these, for example, introduce this green transport EV roadmap, electrical vehicle. There's a green transport network. There's environment-friendly new development area. There's a kind of a new energy like a ferry, like our kind of iconic Star Ferry, still using diesel. But how about E or others thinking? Livable environment, compression emission reduction, clean energy, scientific management. Our study, particular from our kind of university and other research study and regional collaboration within about the GBA area. But the point is, so far, the whole report, I would really praise our EPD colleague to making a very comprehensive plan. But the issue here, we still would not reach the WHO standard. But how a way can we actually thinking about toxicity-oriented goal, rather than to actually meeting the absolute number for the standard? Okay. So that's one leading to we're going to introduce our recent work is consider is because the focus on the toxicity difference rather than total PM concentration. If you're going to re-examine and the issue we have is individual chemicals, because 1 PM 2.5 single particles can carry about 1,000 or even more different chemicals. Can we, if we analyze the chemical from the different source, from different chemical structure, we will understand how much they actually contribute towards this cancer risk, non-cancer risk. In this case, about the left-hand diagram, you can see inhalation cancer risk per million of the population. But even in our own study, we have a study about this PM 2.5 in Beijing and Guangzhou. And then we have a comparable distribution about these trace metals and these pH organic compounds to about generation this reactive oxygen species. You can see how about we analyze almost more than 10 metals. Only 3 metals contribute significantly for iron, copper, and manganese. The rest of the other metals are very minor. But if we analyze all about 20 different compounds pH, but only 2 compounds are contributed significantly. So our major kind of evidence is if we control these toxic compounds, we can achieving much better health outcome even we still actually above, like 90% of population in the world still above WHO like a standard. Okay, so that's the way we're going to, our group engage in PM2.5 sampling in Hong Kong and also beyond, because we're going to understand how this mechanism become about chemical composition, microbial composition, and health outcome. So we have taken sample in the Kowloon urban area, and even very much the background side, including about this very much about the Earth's remote side, including about this offshore location. Consider about Hong Kong is a coastal city, how we interaction with like a marine aerosol as well. Okay, just want to give you an example. I just want to see if you're using electrical microscope to examine this PM2.5, you will see there are many of different shape of particles, and they have different chemical composition. For example, is like sodium-rich particles, sulfur-rich particle, organic aerosol, into about soot, black carbon rich one, metal, or even the flying ash from a coal-fired flying ash. But I just want you to compare two like a city, one into our national sampling scheme, one in Nanjing in the Yangtze River Delta region, one back close to us in Guangzhou in the GBA area. I just want to, the issue is most of our research doing PM2.5, they taking snapshot, in other words, taking sample for 1 week, even for 1 day. But our understanding we need to taking sample for 1 whole year with different season. So if you're going to compare, you can see the pie chart, spring, summer, autumn, and winter up there in Nanjing. Compare with annual data. You can see quite significantly the autumn and winter summer one are two contrast. The pine size depends on the total PM2.5. The different color become about how is their composition, metals, organic, and others, and so far. Even compare speaking, you can see how much difference between Nanjing and Guangzhou. The Guangzhou definitely have a lower concentration PM, and they have different chemical composition than that in the Yangtze River Delta region. So that's we need to really understand, because in the WHO's data, we almost using one single PM2.5 composition as a whole 1.4 billion population data. That's not right, because we really understanding the seasonal and the regional difference. So doing that, I just want to give you an example. Our study actually, one of the 3 sides, we have almost a weekly sampling every single week from the year. One is actually in kind of cross harbor tunnel like side, very close to the central cross harbor tunnel along the Polytechnic side. But that one is into our building. Actually, it's not on the road side, because our apartment building almost summer elevation. We're using about our 6th floor as average inhalation level. And then we also have one of these coastal into some of you hiking know there's Hedrui site in the south of the Hong Kong Island. We have as one of the base for the regional background. It's not local Hong Kong background, but the regional South China background. So you can see about the same pine chart. I use the last slides where you can see spring, summer, fall, and winter. And also you can see the chemical composition, the total concentration. Another thing I just wanted you to focus on, because in traffic related, in the cross harbor one, you can see, I mean, although there's a seasonality, but the seasonality not as big as the ambient in the Polytechnic like 6th floor terrace. But if you go for this background, South China regional background, you will see much smaller like a concentration range, but also they reflect about the major like marine interaction aerosol into the about land-based one as well. Okay, another one is particular if we are in very much on the South China Sea coast as Hong Kong located, we would putting an ambient PM2.5 on different source. For example, in summer, they actually can come over majorly from this marine, whatever from this South China Sea and western of the Pacific. But in the winter side, in the right-hand diagram, they majorly from this land base. In other words, it's come from a polluted air from this around the coast, from this north part of the GBA contribution. So as you can see, we are exposed to major different source of the chemical microbially for about all these different concentration or different component or different toxicity. So putting that way into issue, we can understanding, for example, our component identified from this PM2.5 in the 3 local Hong Kong side, we can see how there are toxic potency for individual compound. And then we have putting about this component resolved PM2.5 can see toxicity. In this one, we're using about the reactive oxygen species, ROS, as an indicator. And then we have putting them into how much relative contribution from this most abundant metal contribute. I just want to quickly highlight, you can see we can explain up to 80% of the PM2.5 induced oxygen stress in the roadside, 65% in the ambient side, but in the background side, we can only explain 30% because there are many of the regional source which are not into our source profile. So in the urban area, heavy metal, particular for the ambient side, for the ROS generation, reactive oxygen species, around about this 20 to 40. But in the roadside, particular, because there are vehicle emission directly deficit there, they have can explain about 45 to 80%. So pH currently very minor because diesel vehicle have reduced significantly, and also about coal-fired power generation plant in recent years from the 2 utility company also lower. So we actually facing currently is a major heavy metal and black carbon one. So that's kind of like our reality here. But we can really calculate how much about this different source combination, total issue with cell toxicity. One of the comparison we have, for example, I just wanted to see we are not bad in consider for most of the city comparison in the world. You can see about our current PM2.5, even about 5 years ago, 2017 is about 22. We are almost the lower end compared about this worldwide network comparison. And also the issue is we are like a sulfate as a majorly organic matter are not is the mostly toxic component as putting there. Even compared with some of Chinese cities like Lanzhou, Wuhan, and others, we are not that bad. But we still consider how about our general population, like health outcome, the regional difference. You can see one of a very interesting aspect, like the PRD in comparison within a YRD. So there's a health outcome significantly different because not only for the total loading for PM2.5, but also the chemical composition, much more like industry-based and contribution source can towards about toxicity for that issue here. Okay. Consider time, I really, this one, our recent work for, we all know, I mentioned about these sour chemicals in the PM2.5. So metals like pH and like others, only this conventional a few compounds. Do we have other compounds? We don't know. Maybe they have a toxicity towards our health. Our recent work is particular from Dr. Lu Yao is we're going to analyze this non-targeted screening for about this further analyze other compounds which not less known to about all of us. So we're going to already have putting out quite a number of the new compounds first time in the AIPM to know their kind of molecular structure, know their concentration, but also we want to know their contribution. So contribution towards the overall toxicity. So in that case, so we already put in some quantification, how much they can actually, this new identified compound, contribute to overall toxicity of PM2.5. But that work is also time consuming. Although we can actually first identify a group of compounds, 10, 20, but if we further want to expanding this kind of effort, we may need for another 5 years, but identify another 200 compounds. But from our sarin compounds, we cannot utilify every single compound. What we're going to use in current in our group is AI-based machine learning. So can we actually, same structure, we're not actually going to testing toxicity one by one. We're going to let machine learning to predict the toxicity. And how then we're going to, using the most toxic compounds, we're going to analyze them again. So hopefully I can probably reporting to our audience within the next few years' time. Another case is if we're going to analyze the toxicity, we want this most of the lab study and simulations most towards our human lens. So the human lens, if we're going to have the ambient particle through our inhalation system, we can reach to our up and the lower retractor system and reach to our lens. In that case, the particles is majorly is a solid or even water droplet is going to deposit to our respiratory system and also on our lens cells. But usually, if we're doing about the cell study, we putting about the PM particle into a small dish, into solutions. Can we actually simulate this really process? We have acquired, luckily, with the university and RGC support, we're getting the virtual cell system, this automatic exposure station. The station, the good point is PM2.5 flow into the cell directly. So the cell only have the medium at the bottom. So the cell actually is our respiratory or lens cell can first direct contact with the PM. We can observe this toxicity or the biological response. So in the same way, and this Yihua's work, we have using this virtual cell system to testing about our real ambient Hong Kong PM2.5. We are using, one is a winter one. You can see about the PM2.5 reached almost 50 microgram per cubic meter. One is a summer one, is only about 15. So you can really observe this kind of yellow bars are significantly causing oxidative stress. And also compare with the clean air, compare with a control side. So this is the first time we have utilized this virtual cell system in ambient study, because this system was designed for the source. You're going to testing them as whatever diesel engine room, you're testing them from other kind of most significant as a source. But and in Hong Kong, the lower PM2.5, we still can observe the cell toxicity into about this ambient air study. Okay, I think I have only a couple minutes. I will speed up for the last part is PM2.5 is not only chemical composition, but if you're going to observe is under the scanning electron microscope, you find bacteria. Anyway, Tong Zhang here, and which actually is our microbial kind of expert, but also we have many of large particles of fungi as well. So in other words, PM2.5 also is a carrier for microbial component. So that's why You can see the study in the past by colleagues who in Beijing can catch about the pathogens and also allergens like bacteria as well. So in doing for this, we just quickly introduce the work. We want this air PM2.5. Can we reflect about this airborne bacterial community because they can travel far away, 700 miles away. So we have taking about a sample both about from our in Asia Pacific region, but we're taking literature data from other study to combine the first airborne bacterial community distribution along the whole planet in the world. So interesting, I just wanted to see, for example, Hong Kong in a subtropical region, we supposed to have a much more diversity than the United Kingdom. But in a microbial world, so the most peak in a middle latitude region, which alongside within about this soil and also with ocean as well. So if you're going to see about this kind of a comparatively urban one, which have a significantly modified in a kind of issue from this terrestrial background and offshore. But if we are putting about the most of the contributor factors, like the source contribution from each of these land, ocean, or air, and which actually is a major contributor of 43%, air quality about 29%. But meteorological condition, either there's temperate region, subtropical region, or other tropical region, they contribute around about 25. So doing this, we really can understand urbanization increase the proportion of pathogen because our inhalation, exhalation exchange about our ambient airborne bacterial community. Anthropogenic impact can destabilize the structure because normally our natural world have its own separation or composition structure. So we can see how about this kind of contribute towards urban and background side. Another way is how about this antibiotic resistance, which actually carried by bacteria or by others. You can see our part from the three study from Jiawen's work were from Beijing, Nanjing, and Guangzhou. I'm not going much into detail considerable time, but you can see the PM2.5 concentration have dropped significantly in the past 10 years because that's the air kind of a pollution control measure. But the situation we observe, there's a kind of a respiratory concentration of pathogen have increased significantly in 19 to 21. That's early our pandemic period. But if there's an issue is because the air pollutant are dropped, so the natural habitat for the pathogen or other bacteria are increased or not, that's we still need about the current new ongoing work to analyze, confirm on this. So anyway, so I'm not talking more is antibiotic resistant. Tong Zhang is our key expert here. But I just want to emphasize one issue. Usually we have emphasized this kind of the left part in the middle diagram is from Tong Zhang's work. We can see on a natural environment, engineering system, and also human animal excreta. But the one case, if we are putting on a human atmospheric interface, so both the relative total abundance and the enrichedness can almost equal or even higher than engineering system. So in other words, at least air can a major contribute towards about exchange from the natural ambient environment and our health through the PM2.5. Okay, so I need to skip on this because we have also analyzed the global urban airborne antibiotic resistance right now on ongoing work. I just want to emphasize one more work because we need understanding what is contribute towards ambient air environment. So naturally, we can see from our wastewater treatment plant. So they are actually is a hotspot from about this quite a number of the antibiotic resistance there, but also we consider about this hospital. They use a large amount for kind of a patient treatment. So both of them can significantly demonstrate they contribute towards about both airborne bacteria, but airborne like antibiotic resistant genes. Okay, another way is less for the air side particular. There are many of the bacteria carry, not only bacteria carry ARG, but this phage, this parasite of bacteria, and even the fringe DNA chips can actually further extend it, particularly for Hong Kong's case, where we can compare 3 cities. So the last one from Zehua's work. So we have about our home cooking, even about this, whatever in a canteen, we have the steamed fish. We actually wanted to see how much, because most of this fish was before they sell into market, they have this antibiotic treatment in a last tank for about a couple of days or a few hours. We want to have an experiment to see if a steamed fish, how much the ARG or antibiotic chemicals can still left after about 20 minutes, 10 minutes steam. But interestingly, they can remove quite a lot in our fish. But there's one of unexpected finding is this steam process have many of the steam out from the hot pot. They can transfer about 30% of ARG and 14% of bacteria count. So unless you have a good ventilation during steam fish, you may expose yourself for the ARG as well. Anyway, so I hope actually I'm going to cover from this like PM 2.5, give you a bit of account from the source emission into the heterogeneous mixture, dynamic and ferric process into the final like the health impact. We're going to see how air pollution reduction, public health benefit, then we can advise our policymaker the best way to control, enjoy the benefit. If I'm going to making about this particular future study we are currently doing is about we need a more integrated toxicity indicator for relevant human health outcome from this PM guideline for more accurate exposure like response assessment and in the urban area. I think Tong also working for the AMR, how we quantify this risk. So we also only explore at the moment is AI-based prediction to facilitate the more like combination about cell in vitro, in vivo animal test, and also epidemiological study for cell animal human coherence, evidence, and transform about the policy recommendation. And then we're going to combine toxicity evaluation both for chemical and microbial component. I hope I actually demonstrate this microbial like kind of a component also play a very key role in our health. I think in almost my last slides, I want to see how clean is air we breathe in the urban area. I think I just want to very 3 simple conclusions. The first one, sustained air pollution control measures have significant effects to lower the concentration and health risk in the last probably 2 or 3 decades in Hong Kong. This actually due to the regional and the local contribution we have significantly putting there. So we know some substance and toxicity which actually can cause our major health outcome. But there are much more is still unknown. That is leaving to our task. Hopefully, we're going to do with the help of our current funding for the project to answer more of that question. So there's more effort are needed to meeting WHO standard, but finding this key toxical component is important because we want to enjoy the best the public health benefit, even we are not reached to this 5 microgram per cubic meter WHO standard. I thinking that's just a group of our members. One photo, there's a new member joining as well. So I thank you very much.